Okay, hi everyone. Today we have our speaker Siqi, who will be talking about zero-knowledge succinct arguments with a linear time prover. Let's welcome the speaker.
Unmute. Okay, cool. Okay, I have no volume here. Okay, cool. Okay, good. Okay, cool. So, by the way, if you have any questions in the middle, please feel free to stop me, and I will start. Okay, so. Okay, so what is okay? Let's because we're talking about construction of zero-knowledge proof and arguments. Let's start by defining them. Though maybe you guys more or less know what it is already, but let's quickly define it. So basically, zero-knowledge proof or arguments are a protocol that receives as common input X, alleged MP statement basically, and there are two parties involved in this protocol. There's the prover P and the verifier V, and the prover also secretly have a witness to the statement X, MP statement X. And then the goal of the protocol is for the verifier to output at the end whether it accepts X as a valid MP statement or not. So this protocol, to be called a zero-knowledge proof or arguments, it need to satisfy at least three requirements. So the first requirement is that it has completeness. So basically, if X is indeed a MP statement and W is valid, then V always accepts, and also soundness. So if X has no witness, then V should reject with high probability. And lastly, like through this communication, the prover's message does not leak anything about this witness W it has. Okay, so basically to measure how good a protocol, basically a proof or argument is, there are three like common efficiency measures that people care about. One is the communication complexity, which is the amount of message that is exchanged during the protocol. And there's also the prover time and the verifier time. So it would be ideal if all three of them are as low as possible. Okay, so I think after I introduce these objects, I want to motivate a bit why we study them. So this is a very kind of classic motivation, which is delegation of computation, in which the V party, the verifier, basically outsource some computation to a more powerful party, which is the P party, prover. What it does is it sends some data that they want to analyze to the prover, and then the prover who has more computation power or has more like maybe patent method of analyzing data or something could efficiently analyze these data and send it back to the verifier. But the verifier does not need to really trust the prover. Therefore, the prover has to prove that it has done the computation correctly. And that is where we would need to use zero-knowledge proof or zero-knowledge arguments. And here, very importantly, the motivation of having low communication complexity and low verifier time is because we want the protocol to be efficient. And also the verifier wouldn't have to done the computation all by itself over again in order to verify this whole computation's correctness. And also the prover time, usually this is not kind of something that people care about, but I want to explain a bit why would we want better prover time. Okay, so imagine this is the diagram. So let's say that the prover have some limit in its computation power. So as the data size that it receives increases, the amount of computation it needs to do to analyze, the analysis cost basically increases. Meanwhile, the cost of proving correctness of computation also would potentially increase. If this increase to like much faster in comparison to the analysis cost increases, what would happen is that this overhead incurred by the proof cost would greatly limit the data size that the prover can process in this kind of delegation of computation setting. So because of this reason, it's ideal for us to find protocols in which the prover's proof overhead is small. Okay, I hope this is clear. Okay, so this is the motivation. Next, I just want to talk about like some existing work and what's surprising to me personally about these existing results. So, so the first I want to talk about is the I mentioned that we care about all three parameters like communication complexity, river time, and verifier time. So how like what's the best that we can hope for? How well can we achieve like some sort of optimal trade-off between these three parameters? Surprisingly, this work by Bootle et al. Shows that, okay, assume the existence of some linear time collision resistant hash family, so some cryptographic commitment assumption. Then there is an NP complete language, R1CS, which has zero knowledge argument that has sublinear communication complexity, sublinear verifier time, and linear prover time. So, okay, let me make some comments here. So all these sublinear or linear are measured with respect to the time complexity of the NP verifier, who would run this like witness in the instance and check whether it is a valid statement and it witness pair or not. So this is how the linear and the sublinear measure is defined with respect to. Is that part clear? Yes.
So RNCS is very close to circuits, right? So the verifier needs to read the circuit to begin with.
Yes.
So the sublinear factor cannot be sublinear in the circuit size, right?
Okay.
There's some preprocessing.
There is pre-processing there, so that's something I will try to hide. I was trying to hide during this talk, but you're right. Yeah. So just to read the instance, the verifier would really need linear time, but there's some like pre-processing that one can do with a trusted indexer object that can help the verifier to not do that, basically. Okay, so and another comment I want to make is actually to achieve just sublinear communication complexity and sublinear verification time is very easy. If you're not concerned about the prover time, because you can use PCP. Essentially, like even a PCP can give you like low communication cost and sublinear and even polylog verification time or logarithmic. I think, okay, polylog verification time, let's say. However, PCP techniques, we all know, like it involves many like using polynomial codes or computer low-degree extension stuff. So that's like quasi-linear time.
That's not true, right?
Okay.
This is not zero knowledge.
Yeah. But I'm saying like even when let's remove the zero knowledge part, I'm saying like even that is hard. Like the efficiency measure to achieve this is non-trivial, is what I'm trying to say here. Yeah. So right, and also it's actually easy if we just want to achieve linear time of prover, because the prover can just send the witness to the verifier and let the verifier do all the work by itself. But that would incur, of course, like linear verifier time. So all I'm saying here is that this trade-off is already quite non-trivial to achieve. So that's kind of what I say when I'm saying like it's a surprise, because you can achieve like all these trade-offs between these efficiency measures. Okay, so but the question that we are curious about is, does there exist a zero knowledge succinct argument with a linear time prover? So what's a problem about the previous construction is that linear time prover is great, but they are only able to achieve like sublinear communication and sublinear verifier time. For argument to be succinct, we usually would like polylog verifier time and polylog communication complexity. So is that doable? Is the question we impose here. And in this work, we show that that is possible. So basically under the same assumption as the previous work, we construct a succinct zero knowledge argument with polylog communication complexity and the polylog verifier time, and also linear prover time. Okay, and the general approach that we follow, okay, is already shown in this Bootle et al. Older paper. This general paradigm is the first. Is as follows. Okay, first one has a linear time probabilistic proof. basically this probabilistic proof has a property that it has like a large communication complexity, like linear communication complexity, but has a very efficient verifier, like a polylog verifier. So the way we reduce this communication complexity is by adding some cryptographic commitment scheme on top, so that we won't need to send the entire proof. We just instead need to send a short commitment of this proof. This is done by the Kilian's method. Maybe some of you guys already know. And after applying this method, we're able to get this linear time succinct arguments in the end. So in the next slides, I will talk about the, yes?
What is a good linear time CRO check?
Very good question. I would say I personally do not actually know the answer to that. Yeah, but like, is there any reason why like even the normally used ones are not linear time?
So a shard 256.
Yeah, is that not linear time?
So linear in the message length, right? Like
Linear in the
hashing.
message lengths, yeah. Or in this basically security parameter that you want. Yeah. I think, yeah, if you don't want that much security, okay. Yeah, it depends on the security parameter you want, let's say. Yeah, so yeah, you don't want it to be polynomial in that, I think, this idea. Okay.
So is this Siqi?
Yeah, this is zero
Good.
knowledge. Succinct is zero knowledge. Yeah. Okay, so if no more question about the result, I will briefly talk about what the Kilian's method look like.
So this is the previous word. I mean the Kilian's method.
Yeah, Kilian's method has been known. It's a general method of compiling. Actually, I will explain here. Yeah. So this is compiling a PCP, probabilistically checkable proof, into a succinct argument. And it's done by the following way. So we start with a PCP. It's a one-round communication protocol in which just the prover send the proof and the verifier probabilistically check a constant number of locations in the proof and output a decision. So that is the PCP. And how this thing is turned into a succinct argument is as follows. So basically, the verifier would sample a hash function from this collision-resistant hash family and send it to the prover. Sorry, this is not showing the slides. I realize it's missing that round. And after the prover get this hash function from the verifier, what it would do is it will construct this Merkle tree. At the very bottom in the leaves is basically the proof string. And recursively applying this hash function to cut the input size by half and build this tree up until it gets to the root, where it just have a very short, basically a logarithmic length a root, and they just send the root to the verifier as a commitment to this entire proof pi. Okay. And the collision resistance property ensures that the prover basically could not lie about, could not have generate a root that does not correspond to this pi being at the bottom of this tree. Okay, so then the verifier would send the query to the prover as before in the PCP protocol, and then the prover would reply with hash, basically the hash pass on the Merkle tree. Basically, that's the pass that in this tree that goes down to the query that the verifier is interested in. And finally, after the verifier receives this, it will check that this is a valid Merkle tree pass, valid Merkle path, and then invoke this PCP verifier on the query answer that it gets and output a decision. So that is a Kilian's method. So basically use this Merkle tree as the commitment. Is this method clear? Okay, cool. So this is about PCP, but here in this work actually, well, I have to say, like, we do not know of PCP with linear length proof and let alone linear time prover. So that is a bigger problem. Okay, I should say there's some caveat, like condition on you have only a constant number of queries. We do not know linear size PCP. Okay, so in this work, instead of considering PCP, we construct something I would say slightly weaker, which is a interactive oracle proof, which allows basically multiple rounds of interaction. And otherwise, it's the same as PCP. At every round, the prover can send a proof, and the verifier can probabilistically query this proof. But they could have interaction, and the later proofs could depend on the verifier's message earlier. Okay, so this kind of object can be compiled in a similar way into a succinct argument, but with more rounds. Okay, so I will not talk too much about how this is done, but just this is basically the method we use to compile this IOP, this interactive oracle proof, into a succinct argument. Okay, so this is a Kilian's method. So from the Kilian's method, we see that really what underlying the succinct argument is really an IOP. And in this work, the IOP that we construct for R1CS is a zero knowledge IOP with logarithmic number of queries and the polylog time verifier and linear time prover. Okay, so these are the parameters that's achieved by this protocol. And I think I need to mention two caveats about this. First is this protocol has constant soundness error, so it's not achieving any subconstant soundness error. And second, it only works for R1CS instances that's over large field. Yeah.
But could the constant be increased by an arbitrary amount?
Sure, but it would influence the efficiency measure basically. So if you want it to be sublinear, then it will blow up the prover time.
Okay.
Yeah. Okay, so, right, so, yeah.
So if for a PCP, do we know linear PCPs where the verifier query complexity is like sublinear?
Query complexity, linear size PCP.
There is no linear size PCP.
I don't think so. I think even the one I know about, like polylog queries, I think the size is like non-linear. It's like n to the 1 plus little of 1. Yeah, but there are quasi-linear lines. Yeah, and the constant, yeah. So yeah, I think even that, I think no, but yeah, I'm not 100% sure though. Okay, so okay, before marching on, I need to quickly define what is this really this like rank 1 constraint satisfiability problem. So this is a problem where the input instance is our matrices A, B, and C, and some vector X. All of these over a certain finite field F. That's why we have that requirement on the finite field in the last slides. So the language, okay, basically A, B, C, X is in this R1CS language if there exists a witness vector W such that its concatenation with X will give you a vector Z that satisfies like A times AZ element-wise product. So this circle means element-wise product between these two vectors. AZ element-wise product with BZ is equal to CZ. So this is actually an MP complete language, and there is a linear reduction from arithmetic circuit to R1CS. So, but just remember, this is kind of asking you to check certain matrix multiplication over finite field. That's what this language is doing. Okay, so I want to talk about some of the related works. First is the results coming from this approach I just talked about, which is using a Kilian's method to compile like IOP and collision resistant hash function into succinct arguments. So on this line, there's the work I mentioned at the beginning, which is the Bootle et al. Paper, where they achieve a communication complexity and verifier time being square root n. And this is the computation size. And their protocol is actually zero knowledge. And later there is the improvement by Bootle, Chiesa, Groth, where they improve the communication verifier time to n to the epsilon for arbitrarily small constant epsilon. But their protocol is not zero knowledge. And in this work, we improve the communication and the verifier time to polylog, and also this protocol is zero knowledge. And I want
the soundness error is
all of them is constant.
Oh, okay.
Yeah, all of them is constant. And all of them only works for large field. I put at the very top, yeah. So subsequent to this work, Lee et al. Actually also constructed a succinct, zero knowledge succinct non-interactive argument actually, where they achieve linear proof of time and log communication. Okay, they have a couple models depending on which model you look. So some can achieve log and the verifier time being polylog. So, but they are operating under a slightly different assumption. So they need to assume that a specific zero knowledge succinct non-interactive argument in the random oracle model, which is secure in the, which is sound in the random oracle model, is also sound when you instantiate this random oracle with existing hash function. So it's a more complicated, or arguably more complicated assumption. Yes.
And then this hash function is also need to be linear time.
Yes, yes, it does. Yeah. So, but essentially, under this assumption, they achieve the same guarantee. This is, I would say, this is quite a different technique. Okay, and okay, cool. Sorry, and the later, this is not results from this approach, but there's some other like subsequent work after this work by Rothblum, Runsway, I think, and also by Bootle et al. That basically remove this constraints over the size of the field and make this linear time succinct argument for R1CS instance over any field of any size. However, there's a caveat that basically the verifier time here in both of these two works are linear. So there's some bottleneck in improving this. So that would be an interesting question to explore. And also neither of these are actually zero knowledge. Although I think there's no real bottleneck that I can see in achieving zero knowledge. It's more like it's not really done. Yeah.
I think there's also like the breakdown and Korean paper.
Okay.
Also follows this approach.
Okay, I see. Breakdown. Yeah. Maybe I read it. I couldn't quite recall, but okay, I will take note of that. Great, thank you. Okay, so these are the related works and that I want to mention. And in the rest of the talk, I want to talk about the techniques behind how to build this interactive oracle proof. But I want to do some simplification. So basically, what we want to build is such an object, basically an IOP protocol with for R1CS instances. So they're at the top, the common input are A, B, C, and W, and the prover secretly also have W. And the protocol want the verifier to output whether it accepts this instance or not. This is I think there are many floating parts in this construction, so it would be too complicated to really fully present it in this talk. So I instead want to just show how to construct an IOP for a much simpler language here. But all the interesting ideas behind the construction, I think, are still there. So I think really there's no loss in this simplification in terms of presentation. So, okay, so the language I'm going to actually focus on is the following language. The language has no input at all. So epsilon, no input. Instead, what it has is the prover have two witnesses, ZAB and ZC, so two vectors. And it want to convince the verifier basically that ZAB is equal to ZC. So this is what the language itself is trying to do. So let me explain a bit why this simplified language is related to the language on the left. This ZAB can be essentially be viewed as this AZ element-wise product with BZ. So it's kind of like the vector you get from doing this operation, and the ZC is a vector you get from multiplying C with C. So these are where the two vectors are coming from, and to build a IOP for this R1CS, we at least need to be able to check this language on the right. Okay. Yes.
But then the prover needs to commit to ZAB and ZC at some point. Right?
Yes. Yeah, definitely. It definitely needs to do that. And Yeah, I will talk about it. So, right, so we'll do this more simplified task later. So, okay, what is the idea behind checking that two vectors are equal? I mean, okay, this is a very like commonly used idea, which is, take the low degree extension of the two vectors, or basically, in other words, encoding them using the polynomial code. If the two vectors are equal, then, if I query this two polynomials at the same point, and randomly at the same point Q, then they should be equal. This is like the short-step lemma that I believe you guys are more or less heard about or familiar with. Yeah, so this is the idea. However, this idea has one problem, which is polynomial codes. To encode a code, to do encoding, you need like quasi-linear time. Therefore, it's not linear time. But we'll somehow still try to use this idea, but implementing it not using polynomial code, but using something else. Actually, is the idea clear? Okay, cool. So the implementation is done instead by what's called by like a dimension T tensor code. So let me explain quickly what's the tensor code. So this diagram here illustrates a dimension 2 tensor code. So what happens is when I want to encode a vector ZAB with high dimensional tensor code, I write it as a cube or a dimension T cube. In this particular case, in dimension 2 case, I just write it as a matrix. And then I encode it along each direction sequentially. Let's say I first encode each row with a linear code, and then encode each column with a linear code, and eventually get this matrix at the end that's larger in dimension, larger in size, larger in size. And one property of tensor code is that in each row and each column are all code words of some base code C. Okay, and this can be done in linear time if the code that we use to encode each row and each column are linear time encodable code.
Well, why would that be 5 times 5?
Times 5.
Right.
Oh, I mean, I'm just okay. This. Oh yeah, you're right. Actually, it should not be times 5. This should be yes.
Okay.
That's right. There should only in this green one there should only be 1, 2, 3, 4.
Yeah, it should be
four columns. 4 columns. Sorry about that. Yeah. Okay. So this is the tensor encoding, and then now what we treat this code word as is the following. Basically, this final code word here, we view these as basically the coefficients of some multilinear polynomial. Okay, imagine that this encodes the coefficients of some multilinear polynomial. And now what we do is we still want to query this polynomial at a random point in the field. However, since these are not really the evaluation table, as in the polynomial code, it's instead the coefficients. So what we need to do is we actually need to take an inner product of this coefficient encoding with some like rank 1 tensor of the form x1 through xt. So this inner product should really be thinking of as just evaluating this low degree polynomial at a random point q. Okay.
Wait, how do you do a inner product between a matrix and?
I view it as a vector, or like it's more like this itself is, for example, like in dimension 2 q would be x1 tensor x2. So what happens is you will left multiply with x1, right multiply with x2.
Oh.
So you multiply each dimension with one of the component in the tensor.
So Q is also will act like a dimension T tensor and it takes the inner product.
Yes, yeah, their dimension matches, right? So if this is a dimension T tensor, then Q is also dimension T, and they matches, right? Oh, good. Okay. So this is the general idea, and how we implement it is the following. So now we still have the prover, verifier, and prover have these two vectors. And then the prover was sent to the verifier, basically this tensor encoding of the two witness vector. And then what the verifier would do is the verifier would sample a random query Q and send it to the prover. and the prover will reply back the evaluation of the inner product, two inner products back. So, but of course, okay, we could not trust the prover anyhow. So there need to be some like a soundness check. And the soundness check involves two steps. First is to check that the encodings EAB and the EC are actually done correctly. Basically, this is achievable because tensor codes are locally testable. So we can do this, and this is doable in linear time. And the second part we need to check is that the inner product actually computed correctly. I will not really elaborate on that. That's also a very interesting part, but let me just say that with some auxiliary proofs, one is able to check relationships like this in linear time. So I guess you guys have to trust me with that in this talk.
So what does the first step mean? Is that
The
a
first step?
commitment? No.
Oh, the sending. It's not well, you can. It's basically sending oracles to the prover, verifier. So it's not quite a commitment because it actually sends the entire thing, right?
Wait, but
yeah,
that incurred high communication.
Right. Proof itself has high communication, and when we use the like Merkle tree to convert it into a like argument, that will have no communication
So
cost.
you're not worried about it.
Yeah, so in the proof, we're not worried about communication costs. We just worry about the prover and verifier time. Yeah.
Is the EAB and EC sent to the verifier or not?
It's sent to the verifier as oracles. Yeah. Okay, and the second step, the consistent, like trying to check whether the soundness check part of this protocol is where actually the verifier would query this EAB and the ECs. Okay. Yeah.
It's T, did you like say?
It's a constant.
It's not a-
Yeah, it can be any constant, but yeah, but we cannot afford to make it a super constant, basically, yeah. Yeah, so essentially, the one thing I want to note here is that actually this verifier makes queries to EAB and EC. And I talked about how EAB and EC are like dimension T tensor code words. Dimension T tensor code words can be thought equivalently as a collection of like a bunch of dimension T-1 code words. Okay, so it's just like a matrix. I can think about it as a collection of columns. In the same way, I can think about it as a collection of dimension T-1 tensor code words. And what we do is, the query pattern that we have here is that we actually only make one query to each of the dimension T-1 tensor code words. It might be a bit confusing, but I have to introduce this because of some requirement on the construction later. Yeah. Okay, since this probably doesn't mean much, I will just go through it quickly. So this IOP, I want to note that it's not zero knowledge because of the following reason. So when we make queries to the EAB and EC, there potentially the verifier is learning knowledge. Is learning like information about the witness W, because witness W is used in computing this VAB and DC. And when we're doing the encoding, the information is still there in the code words. And it's possible that the step of querying really tells the verifier something about the witness. Okay, so we need to resolve this in order to make this protocol zero knowledge. And the solution is actually, okay, pretty, I would say pretty straightforward, which is we encode doing this encoding not with any general tensor code, but rather with zero knowledge tensor code. Essentially what it does is when you make only bounded number of queries to such a code word, you learn nothing about the underlying encoded message. So it might be a bit counterintuitive that you're not learning anything about W, but you're able to verify that this computation is done correctly. But I think that's a general confusion about zero knowledge proof that, yeah.
Could you explain what is semi-honest verifier zero knowledge?
Oh yeah, that's a good question. Basically, semi-honest verifier zero knowledge means that for a verifier that follows the protocol entirely, it shouldn't be able to extract any information from the message and from the queries it reads during the process. On the other hand, a malicious verifier basically can do whatever. A malicious verifier can even read the entire EAB and EC. Like we have no control of like what the verifier is doing. I mean, honestly, when they can do that, there's really no way that we can hide anything from it because this has to be an encoding of this vector ZA, B, and ZC. Yes?
How is this different from honest verifier zero knowledge?
Honest verifier, I think wait, zero. Okay, I'm
Well,
not.
if the verifier is honest, then you don't need ZK.
I feel I'm never
So
quite.
honest versus malicious there, it's like whether the verifier samples the challenges at random. Like malicious verifier might sample challenges in a non-random way.
I see. But this semi-honest would also sample it in the honest way. So I saw the semi-honest and honest means the same thing, because if the verifier is fully honest, like it doesn't even analyze or read into the message, then there's no way we can learn anything. So I think honest also means semi-honest here, like try to analyze its message, its view. Okay, so yeah. So okay, yeah, as I said here, the solution is to use zero knowledge code, and basically, so what kind of zero knowledge code could we like? It suffices for us. What's the requirement on the zero knowledge code? So a couple of requirements. First, zero knowledge code, it need to be linear time encodable, and also it needs to be a t-1 dimensional tensor code. It also has like constant relative distance and constant rate. Okay, so all these like kind of basic requirements on a good linear code. And secondly, it need to have this zero knowledge property, which essentially says, okay, if I read one entry of this linear code, I learn nothing about the underlying message. So that's a simple to state requirement. And finally, we want this to be explicit. So what that means is you can understand it as basically this, this code word have very succinct description. Its generator, the generator of the code word has a very succinct description. This requirement is because of some step that I will hide from you guys, which is later we'll need to do proof composition. Because so far the protocol I introduced to you guys still have relatively high query complexity. And to reduce the query complexity, we need to do proof composition. To do the proof composition, basically, all the things that decide our outer instance, for example, the generator matrix of this code, need to have a relatively small description. I could not just give a like length n description of this code. Okay, so that is where that part is needed. So if a zero knowledge code satisfy all these requirements, then it suffices. It will help us to construct a semi-honest verifier zero knowledge IOP. And from that, we can actually construct a malicious verifier zero knowledge succinct argument. I can explain quickly like why you can guarantee like security against malicious, zero knowledge against malicious verifier in the succinct argument case. Well, it's kind of because whenever the verifier wants to make a query in the succinct argument, it needs to send the query to the prover. So if the prover detects the verifier is trying to ask for more than it should have, then the prover essentially can just abort, and that will be secure. So that is the reason.
Wait, but if the verifier is sending non-random query, how do you detect that?
This is not a hazard here. Here, this is a kind of a worst case guarantee. Like it's not saying reading a random entry, it will hide the message in. It's more like saying, oh, reading any bounded number of entry, we can hide the message. So here in this specific protocol, we don't care about whether the verifier is randomly sampling the entries or not. Okay, cool. So how much time do I have? 5 minutes. Okay, great. Then that's enough time for me to say like quickly, basically how we construct this. It's going to be a bit boring because, okay, honestly, it's just one query zero knowledge code. I think most of you guys might already have an idea in your mind how to construct this. Basically, the idea is to use a split code, which is very simple. So first, to actually achieve zero knowledge, we have to use randomness. Okay, otherwise everything is deterministic. Of course, every bit will reveal something about the underlying message unless it's a useless bit. So what happens here is we add we encrypt it using some randomness R, and what we do is we encode this. Sorry, did I say encrypt? I meant to say encode. Okay, we encode this X with some explicit linear code. Okay, and then we mask it with some randomness R, and then concatenate with R. So it's clear that every bit of this thing is really random if you just read one bit, right? So it's quite simple. And this actually is the code that, yeah, that is explicit that we use. And okay, because we're requiring like really the zero knowledge code to be tensor code, we also additionally show that actually this zero knowledge property is preserved under taking tensor product. Specifically, if C, the base code is a B query zero knowledge code, then C tensor T is also a B query zero knowledge code. One small comment here is that experimentally, actually, we see that say C tensor T is actually B to the T query zero knowledge, but we weren't able to show that. So I think it's also very interesting to show it, although I don't have an application. Yeah.
How do you experimentally test it?
You can code some small instances and basically look at the distribution of a bounded number of bits, right? Yeah, if it's uniform, then yeah. Oh, no, okay. So sorry, I saw you have a question, never mind. Yeah, so okay, all these is just saying like there actually exist explicit one query zero knowledge tensor codes. And using this, we're able to construct the ZK IOP and also the succinct arguments. Okay, nothing sounds very exciting here because it's one query, but I want to say quickly at the end that actually I think zero knowledge code are objects maybe of their independent interest outside this construction of succinct arguments. So there are a couple of things we're able to show about these zero knowledge code that is really not needed in our construction, but I just want to briefly talk about it in case anyone is interested in working on, in studying this object. So one thing is actually there do exist zero knowledge code with linear number of, where you can basically, when reading linear number of the entries, you learn nothing about the underlying code word. The construction is based on what's called a linear uniform output family. This is not explicit, so I think it's still very interesting to me, at least, that can we give explicit construction for such code words? And yeah, okay, there's some linear algebraic characterization of zero knowledge code, but I really don't have time to touch on that. So if any of you are interested, we can talk about it offline. I think this is actually, yeah, this is, I think it's pretty interesting characterization. It seems to be connected to certain ways people are constructing locally testable codes nowadays. Okay, so finally, I will just talk about the open questions. I think all of them I more or less mentioned already during my talk. The first one is like, okay, I just talked about explicit constructions for these large number of query zero knowledge codes. And also I mentioned like, can we show that the zero knowledge, basically when we tensor the code, the zero knowledge query bound also grows exponentially with this dimension T. And lastly, this is the open question I talk at the related work section, which is about can we reduce verifier time complexity for those IOP protocols, for those IOP for R1CS over small field. Can we do better than linear verification? Okay, that'll be it. So yeah, thank you.
We have time for 2-3 more questions.
Yeah, so back to the constant error soundness.
Okay.
If you want to reduce the soundness error to something like 1 to the 2 to the kappa, you just repeat the protocol kappa number of times.
Yes.
Sequentially. So why are the results not stated for negligible soundness or exponentially small soundness? Because you only incur like a kappa blow up in the complexity of everything, right? And kappa is a constant, I guess.
Okay, okay, but that, okay. When I
don't
say-
even want, somehow you would consider kappa n as not linear time.
Yeah, I think kappa times n wouldn't be considered linear time. It's more like gamma.
Do you think then for linear time, fully linear, is there a possibility to result for like
I don't.
non-constant sumness?
I actually don't know of impossibility results in my work. I'm not sure about the answer there. Yeah. Yeah, that wouldn't be linear time.
So practically purposes kappa is fine. I mean, anyways, the zero knowledge construction, when you transform it into arguments, there are security parameters floating on everywhere.
Sure, but I think they are like additive to n instead of like multiplicative to n. So
Even for your zero knowledge argument, that doesn't sound like when you use CRHF, right? So you would end up with a prover that runs in time order t times polylambda.
order
That's why
but-
you need linear time hashing, but it's still t times order of t times lambda, right?
but lambda is your input size, right? So like when you do the hashes, you would chop them into chunks of length lambda. So I think it's still additive overhead instead of multiplicative overhead.
No, the CRHF, the security parameter for CRHF, that should show up in the complexity.
It should. Yeah, but
So
I'm
you're
saying it's
that that's
additive.
just additive.
Yes, yeah, it's additive.
There aren't many examples of linear time hash collision resistant hash, right?
Okay, I'm not sure about that, but yeah, maybe you're right. I'm not very well versed in this literature. Yeah.
Yeah, otherwise the theorem would have been like assume DDH.
Okay, sure. Okay, that yeah.
And like maybe one final question on zero knowledge codes. So the result that you had, which kind of showed a more that it was zero knowledge. You had a code which was zero knowledge against one number of queries, right? So I was wondering whether you guys thought about the phase transition between local decoding to zero knowledge, in the sense that you want the code to be locally decodable in like t queries, but if you make like t by 2 queries, it still remains zero knowledge. Is that something you guys thought about?
I didn't understand what's this phase transition. Okay, I don't see the trade-off between locally decoding and the zero knowledge.
Right. So local decoding is that you make t number of queries,
Okay.
and you're able to still decode.
You're able to decode. Okay.
Whereas zero knowledge is that you make t prime queries, but you learn no information. Right. There has to be a phase transition somewhere, right? From t
I see.
to t.
I see. So in our work, I think these two numbers are in different regimes. So they're far from meeting in the middle. So we didn't consider this. Yeah. Because I mean, to decode, you literally still need to read sublinear number of bits in this case. Sorry, entries in this case. Well, when we are guarding against things, we actually just guard against one query. So it's a different regime. Yeah. Yeah.
I think maybe another feature is that the code construction here does not need to be locally decodable. It just needs to be linear time decodable.
Yeah, it's okay. It depends on what the mean to be local. But if you count as sublinear, yeah, it doesn't need to be that local. That basically, let's say. Yeah, you're right. Yeah. Okay. Nice.
Okay, if there are no other questions, let's thank the speaker.